Alright, welcome to the first of hopefully many videos helping you guys out with some of your mastering engineering problems. What I'll be doing is going and looking to see which problems you guys are having the most difficulty with, and the purpose of this video solution is to give you a little bit of assistance and a little bit more insight. So for your second homework, I noticed the ones you guys missed the most was the dot product. So first I'd like to say the difference between the math that you learn in your mathematics classes and the math that you use in engineering is absolutely nothing. In math, you're just dealing with a whole bunch of numbers and they give you a little bit more insight on how to do it. In engineering, you're actually applying those to like forces or velocities, a whole bunch of different vectors that you'll come across. But this is more focused on the dot product. I'd like to review a little bit of the dot product. So we have a force, and that's basically your F dot U, where U is your unit vector, and this kind of breaks a little bit farther into the magnitude of F with your unit vector and the cosine of an angle. So your UA is your unit vector, and your angle theta is the angle between the vector and its direction. I'd like to apologize in advance for my handwriting. I'm an engineering major, not an English major, so please forgive me. So in this problem, the first part is part A, and in part A, you're asked to find the components of the force P, and you're given its cosine angles. Just a little quick review of the cosine angles. Color back to black. So you've got your Cartesian coordinates where you've got an x, y, and a z, and then you've got some force pointing up this way, and you'll have an angle alpha, which is in between your force and the x-axis. You'll have an angle beta, which is between your force and the y-axis, and then you've got another angle gamma, which is between your force and your z-axis. So, breaking these things down into components. So the first one is, we'll just start with the x direction. So you're given the force P, which is equal to 45 newtons, and you're given your angle alpha, which is 150 degrees, your angle beta, which is 80 degrees, and your angle gamma, which is equal to 60 degrees. So let's write the above equation down here. So we have the magnitude of P times UA cosine of alpha. Now when you're given the cosine angles, this is kind of large, so the important thing to keep in mind is that this unit vector A is in the same direction, so this is just going to be equal to 1. So your equation sort of simplifies to just P, magnitude of P, cosine of alpha. So in the x we have 45 times the cosine of alpha, which we'll just go ahead and write the number in there, which is 150, and that is going to be equal to negative 38.97, and that's in newtons. So let's go ahead and apply this above part to the y and z directions. So we have P cosine of beta, which is going to be equal to 45 times the cosine of 80, which gives us 7.81. That's newtons. And then we have the z component, which is magnitude of P, cosine of your angle gamma, which is going to be 45 cosine of 60, which is just 22.5 in newtons. So you might look at this and you might figure, well, why is x never negative and the other ones are not? Well, if you can kind of mentally position yourself above the xy plane, so you have your x-axis here and your y-axis here, and you've got your force coming off this way. Try to make it fairly accurate. So this is going to be your force P, and this is going to be your positive directions, y and x. So your angle here is given as 150, and you can see that obviously P is pointing in the negative x direction. And then you're given your other angle, kind of kill two birds with one stone, beta, which I believe is 80 degrees this way, and that is going off into the positive y direction. So there's part A. Go ahead and start a new page here. So for part B, you're trying to find the angle in between F and P. So let's go ahead and start by writing out the dot product for F and P. So you're given F dotted with P is equal to magnitude of F times the magnitude of P times the cosine of the angle between them. And you're trying to figure out what this angle is. So doing a little bit of rearranging with this equation, we're basically just going to take this, throw it over there, and then take your inverse cosine. So your angle theta is going to be F dotted with P divided by the magnitude of F. Well, let me scoot this over a little bit. So we have F dotted with P divided by the magnitude of F and times the magnitude of P, and then you're going to take the inverse cosine of that. But we've got to do a little bit of work before we can actually get there, because F is given not in the above cosine angles, but it's actually already given to you in all of its components. So for the dot product between two vectors, let's look at the dot product definition again. So let's just do it generically at first. So you have M dotted with N, which is the same thing as M, it's supposed to be M, times N, keep in mind these are magnitudes, times cosine of the angle in between them. And when you kind of break this down into their various components, this cosine of the angle in between them just kind of turns out to be 1, because when you do components, well, let me go ahead and write this out all the way first. So you'll have m in the x times n in the x plus m in the y times n in the y plus m in the z times n in the z. And like I said before, with dealing with this the reason this cosine theta kind of drops out, because both of these are in the same direction, and when you've got, let's give it an x and a y here, so you've got a force m in the x, and then you've got another force n in the x, and you can kind of see already that the angle in between these two is 0. Cosine of 0 is 1, so this term just kind of drops out to be a 1. So let's kind of apply this to F and P. It's kind of handy that they've already given us the components of F. So let's go ahead and write this out for f and p. F dotted with p is going to be the component of f in the x times p cosine of alpha plus f in the y times p cosine of beta plus f in the z times p cosine of gamma. So that's all nice. I know you guys are engineers and you like numbers, so we'll just go ahead and write this out. Actually, let me go ahead and write out f. So they're giving you f is equal to 3.6 in the I, O minus 13.5 in the J, and 28.6 in the K direction, and these are all newtons. Now you guys should get fairly comfortable with IJK notation. It's just fancy words for saying X, Y, and Z. So applying this to the above, we have F dotted with P is going to be 3.6 times, I'm just going to go ahead and use the numbers that we found up here. So we have a negative 38.97 plus a negative 13.5 times 7.81 plus a 28.6 times 22.5. And when you do all the math out here, you can kind of see that this is going to be the dominating one. Even though that these two are negative, this is going to kind of dominate it and make it a positive. So this is in 140.296. This becomes a negative 105.491. And this is a positive 643.5. And this just equals 398. So there's your F dotted P. So now let's go ahead and, well, we're not exactly ready to throw this back into the above equation right here, because we still need the magnitude of F. F is given in its component form. So simple square root sum of squares will give us the magnitude of F. So F magnitude is equal to the square roots of 3.6 squared plus 13.5 squared, 28.6 squared. You'll notice I didn't put the negative in there because when you square negative, it becomes positive, so it doesn't really matter in this case. So when we do that, it equals a 31.8303. Now that we've got all our components for our equation, we're ready to actually throw it in there. So let me just write it down here to kind of remind you guys of what it was. We're looking for the angle theta, which is the inverse cosine of f dotted with p, f dot p, magnitude of f, and the magnitude of p. So now that we know what this is from up here, we know what this is from over here, and p is given in the problem already. We can go ahead and throw some numbers in here. So angle theta is going to be the inverse cosine of 398 divided by 40. Let's stick with my notation. 31.83 times, what was it, 45. And when you do that, you get an angle of 73.9 degrees. So there's part B. Now part C is getting a little bit more into the meat of things. and it's asking for you to project a force onto, will determine the magnitude of FDA along the member DA due to the force F. Now that's a very fancy way of saying find what part of F is acting along the member DA. So let me see if I can't pull this up to make it look a little bit better. Sort of help out my description a little bit. Okay, so this is what you're looking for. You've got this force F right there, and you're trying to find out what part of this is acting along this member AD. So again, we're going to be using the dot product to figure this out. So, and they're just looking for the magnitude, so we're going to say that the magnitude, well, let's write out the dot product for, so F dotted with dA is going to be equal to the magnitude of F dA times the magnitude of dA times cosine of the angle in between them. And since the force dA and dA are in the same direction, because we're looking for the force this way, this would be FdA. This cosine, the angle in between, just turns out to be 0, so this just kind of comes out and goes into 1. So we're looking for this guy right here. So do a little bit of algebra and move this guy over there. We turn out that the magnitude of FdA is going to be equal to the dot product of F dot dA divided by the magnitude of dA. Well, that's all great and fun and dandy, but first we need to, try to figure out some positional vectors for dA to get some numbers to throw in here. So to find position, we are given 2 points. We're given the point of A and the point of D. So our position coordinates so we have D is equal to 0, 2.76, 3.5, and we have A is equal to a negative 4.36, 3.63, and 4.26. So now if you guys remember kind of how to do this, what we're doing is finding a position vector. And to get a position vector, what you need is destination minus origination. And you can see that A is going to be our destination and D is going to be our origination, dA. So in order to do this, our position vector dA, let's go in the x direction. We're going to have a negative 4.36 minus 0. In the y, it's a funky looking y, but that's okay. Put a comma. We have 3.63 minus 2.76. And in the z, we have a 4.26 minus 3.5. So when you do a little bit of math, this turns out to be just a regular minus 4.36 in the I, plus 0.87 in the J, plus 0.76 in the K direction. Alright, so there's our position vector. So now we're looking for Now we just need the magnitude of dA. So the magnitude of dA, and that's the same thing as when we found the magnitude of the force, so it's just going to be a square root sum of squares. So we'll do the square root of 4.36 squared plus 0.87 squared plus 0.76 squared, and that's going to be equal to a 4.51044. And remember that this negative becomes positive when you square it, so I just didn't even write it in there. So now we're ready to use our above equation right here to find the magnitude of F of the force in the dA direction. So I'm going to write this out a little bit in a little bit of a longer format. So we've got the magnitude of F dA is going to be equal, we'll do this symbolically first. So your force in the x direction times dA in the x direction plus our force in the y direction times dA in the y direction plus Fz times dA in the z direction. And all this is just an expanded out version of the dot product. Because going back up here, we need that in our numerator, F dot of dA. So let's make a nice little line, and we can move on to the denominator, which is just simply the magnitude of dA. So now that we know all of these, we know all the components of our force in the x, y, and z. We know all the components of dA in the x, the y, and the z. We just found that out right here from our position vector. And we just found dA by doing square root sum of squares. We can go ahead and figure out what this is going to be. So now that I've done it symbolically, let's do it with some numbers in it. Everybody likes numbers. So this is going to be 3.6 times a negative 4.36 plus a negative 13.5 times 0.87 plus 28.6 times 0.76. Oh, that's supposed to be a 6, not a 2. 6, and that's all up in our numerator. And then our denominator is just going to be the magnitude, which is 4.51044. And when you do the math, the magnitude of F dA is going to be equal to a negative 1.26484, which is, when you do sig figs, it's just going to be a negative 1.26, and this is in newtons. Alrighty, that's parts A, B, and C, so let's go ahead and move on to part D, which is probably, which I saw was the most confusing to a lot of y'all. And in part D, they're asking you to find the components of the force perpendicular to the direction. So instead of me writing this out, I think I'm just going to snip it in here, so give me a second. That's not what I wanted. Cancel. Part D, here we go. And come on back. Okay, so in part D, they're saying find the component of a force perpendicular to a direction. So they're saying given this force that we've been working with, find the component of x that acts perpendicular to the member dA. Vector addition of the perpendicular and parallel components. This is just basically saying you take the parallel and then the perpendicular, add them together, and you get F. And they would like us to write our answer in component form. So I'm going to kind of write this out a little bit. So we have our total force, F, is going to be equal to the force parallel plus the force perpendicular. And we just found the force parallel in the above problem, well, the magnitude of it. So this is really just equal to the force is equal to F dA plus F perpendicular. So the force perpendicular is what we're trying to find. We already know what the force of dA is, and when we're given our force. So we'll do a little bit of algebra here and we see that the force perpendicular is just equal to our force minus F dA. And since we're using forces, we got to keep in mind that you can't just add forces together, you have to add their components. So we already have the components of F, and now we just need to get the components of F dA. We've already got the magnitude, but not the components. So let's go ahead and get our components. And you can do that, the easiest way to do force components is just your force times your unit vector, and that'll give us our force in the x, force in the y, and our force in the z. So we need to come up with a unit vector and get the components of F dA. So let's start out by F dA is going to be equal to the magnitude of F dA times our dA position vector in x. We're going to divide this by the magnitude of dA. That'll give us our direction in the I. And then we need the magnitude of dA times dA in the y direction divided by the magnitude of dA. It's getting a little repetitive. dA in the z divided by the magnitude of dA. So we already know all of this. We found these in the previous problems. We found this from the position vector. We know all of our dA components in the x, y, and z from our position vector. We know what the magnitude is by taking each one of these and doing a square root sum of squares. So since I already have all these numbers, I'm just going to go ahead and write them in. So we have a negative 1.26 times negative 4.36 divided by 4.51. We have a negative 1.26.87 divided by 4.51. And we have a negative 1.26.76 divided by 4.51. Put some equals down here. So now we get that this is equal to a 1.22 in the I minus 0.244 in the J and a minus 0.213 in the K. So now that we have the components of F dA, we are ready to go ahead and solve this for our first our force perpendicular to our member DA. So I'll write it out symbolically again. So we have our force perpendicular is going to be equal to F into X minus F dA in the X. Sorry about all these subscripts. In the I plus F in the Y minus F dA in the Y. Got subscripts going on here. Plus F in the Z minus F dA in the Z. That's going to be in the K direction. So F perpendicular is equal to a 3.6 minus 1.22 in the I, and we have a negative 13.5 minus a negative 0.244 in the J plus 28.6 minus a negative 0.213 in the K. So do some simple addition here. We get that our force perpendicular is going to equal to a 2.38 in the I minus a 13.3 in the J and a positive 28.8 in the K, and this is all newtons. So there's the dot product, hopefully explained a little bit better. Just to kind of give you a little foreshadow of why this is important and why you need to be doing this and how this is going to be helpful later on when you get into classes like, say, mechanics and materials, and you're looking for, axial forces. The axial forces, you've got a member, and it's just the force acting along its axis. And then you're worried about bending moments, so you've got some member, and you've got force going this way, and this thing is, some dimension from here to here. You can figure out your bending moment from your F perpendicular, and then you can figure out your axial force for F parallel. You guys will worry more about that when you get into mechanics and materials, but just to give you a little oversight of why this is important and how this is going to be helpful later on, there it is. Okay. Now I just got to figure out how to stop this. Cancel. Where did my little thingy go? Where is the stop button? That's not it. Huh. My stop button has gone away. Here we go.